Auzubillahi minash-shaytanir-rajeem. Bismillahir-rahmanir-rahim. Assalamu alaikum class. I hope everyone will be okay and enjoy good health. So this is lecture number 16 for the course of partial differential equation. In today's lecture we will discuss the conversion of first order partial differential equation into uh, canonical form, and then we will discuss that why the conversion to canonical form is important, and how it is helpful in order to solve the give some given first order partial differential equation. So first we will discuss the general procedure of the conversion, and then we will apply the procedure into on some problems. Okay, so let's consider the following first order partial differential equation. The general form of the first order PD is given by this equation: uh, a coefficient P which depends on x and y multiplied by ux, a coefficient Q multiplied by xy, Q which depends on xy multiplied by the derivative of u with respect to y, is equivalent to some term which contains u and a function s. There are two types of quantities in this equation. One quantity is the quantity u which depends on x and y. You can see here from the subscript notation, u x means the derivative of u with respect to x, uy means the derivative of u with respect to y. It means that the unknown function u is dependent on two variables x and y. The second type of the quantity is P, Q, R and S. These are also functions of two variable. They may be constant, they may be variable, they may only depend on X, or they may only depend on Y. There are various possibilities for all these four quantities. And the special thing for these quantities is that these are all given quantities. Okay, so we will try to convert this problem to canonical form, which is all sometime canonical form is also called the normal form of the PD, and of course the canonical form is much more easier to integrate and to construct the solution. The following steps which I am going to present is only applicable to problems of this type. Okay, you can, if your problem is of this type, you can apply this procedure. If your problem is something different from this equation, you cannot apply these steps. So we will discuss the procedure step by step. Before going to the details of the procedure, let's just study about the quantity which is known as Jacobian. So the standard definition of the Jacobian is for two function xi from r square to r and eta from d, which is a subset of r square to r. Note here that the domain of xi and the domain of eta is same. So the Jacobian of these two functions xi and eta is defined by this determinant. It is denoted by capital J, which may or may not depend on xy, is equal to determinant of this matrix. This matrix contains four entries. In the first row, you will write the derivative of zeta with respect to x and the derivative of xi with respect to y. In the second row, you will write the derivative of eta with respect to x and the derivative of eta with respect to y. This is called the Jacobian of these two functions xi and eta. So there are various possibilities. Jacobian may be 0, it may not be 0, it may be positive, it may be negative. Okay, so let's try an example and find the Jacobian of two function. Let xi is equivalent to x plus y and eta is equivalent to x. Now, what is the Jacobian of these two functions? The Jacobian of these two functions is zeta x, zeta y, eta x, and eta y. So xi x is basically the derivative of xi with respect to x, which is I think 1. If you differentiate this expression with respect to x, you will get 1. Similarly, the derivative of xi with respect to y is of course 1. The derivative of eta with respect to x is 1, and the derivative of eta with respect to y is 0. So if you calculate this determinant, then the value of this determinant is -1, which is non-zero, which is not equal to 0. In some cases you may have the determinant equivalent to 0. Okay, as there are a lot of possibilities. In this lecture and in this method we will be interested in Jacobians and non-zero Jacobians. Okay, if the Jacobian is non-zero, then it means that both of these functions are okay. If this is 0, if for some functions the Jacobian becomes 0, we will reject these functions and we will say that these functions are not okay. Okay, so this is basically the technique of calculating the Jacobian of two functions. Now let's discuss the conversion of FED to some canonical forms. The standard form or the general shape of the partial differential equation is P ux plus q uy plus ru plus s of xy. So the first step is that you have to make the Lagrange subsidiary equations. How can you make the Lagrange subsidiary equation? You can write these identities. Dx, the first term is derivative with respect to x, so you will write dx divided by p, the coefficient of ux. The second derivative is with respect to y, so you will write the uh, uh, dy divided by the coefficient of uy. So the third equation is du by r, which is the coefficient of u in the right hand side. So this setup equation is called Lagrange subsidiary equations. You will only consider these two equations and you will reject or ignore the third identity. Okay, you will select the first ratio, the first two ratios of these Lagrange subsidiaries equation, and you will then solve it. So if you note that p is a function of x and y, see here q is a function of x and y also, and here is a quantity dx and dy. So upon integration it is possible, but I think it is sure that you will get a solution in terms of x and y. So you will write the solution of this ordinary differential equation as zeta of xy is equal to c1. By solving this identity, you will collect this function zeta of xy is equal to c1. You will fix it to some constant. Okay, now the next step is to you have one characteristic curve. The next step is to select another characteristic curve, keeping in view that the Jacobian of xi and eta must not be equivalent to 0. You must select the eta in such a way that the Jacobian is not equivalent to 0. Okay, you can use eta is equal to x, or you can use eta is equal to y, you can use eta is equal to x plus y, but the most simplest case you will select eta is equal to y, and you will be amazed that it will always work. In I think 99% cases, if you select eta is equal to y is equal to c2, then your Jacobian will be non-zero. So when you get these two functions, xi and eta, and you find that the Jacobian is non-zero, so you are ended up with step 3. Now you will follow step 4. So first recall that the equation, uh, in this equation x and y are independent variables. In the next step we will change the independent variable x and y into zeta, into xi and eta. Is it clear? We will replace the independent variable x and y into xi and eta. So if we change these two variables, we at the first step we have u as a function of x and y. So if we change the x and y into xi into eta, we get u as a function of xi into eta. Now we will check that what is the partial derivative of u with respect to x and what is the partial derivative of u with respect to y. So calculating, so if u is a function of zeta and xi and eta, then the partial derivative of u with respect to x can be calculated using the chain rule. You can apply the chain rule. U depends on xi, u depends on eta. Also I am trying to calculate the derivative of u with respect to x, so I will apply the chain rule. I will calculate the derivative of u with respect to xi and then multiply it with the derivative of xi with respect to x. Similarly, we will do the same thing with eta. Uh, Partial u or partial eta into partial eta over partial x. This is the application of the chain rule here. So if u is a function of xi and eta, then u x will be u zeta x plus, sorry, u xi x plus u eta into eta x. Now we have to calculate the value of uy. So u is again a function of xi and eta, so uy will become the derivative of u with respect to xi into the derivative of xi with respect to y plus the derivative of u with respect to eta into the derivative of eta with respect to y. So our next step is we have to substitute this equation into our main partial differential equation. So put the value of ux and the value of uy in this problem. So you will get an expression of the form u at xi means the derivative of u with respect to xi plus some function of xi and eta multiplied by u is equal to some function of xi and eta. When you substitute the values of ux and uy in the standard form of the PDE, you will get an expression of this form. This expression is called the canonical form of the given partial differential equation. You may note that this is a simple ordinary differential equation. Means there is only the derivative of u with respect to xi. So the other variable eta will be treated as a parameter or a constant. If we are trying to solve this ordinary differential equation by integration, by integrating factor, we will treat eta as a constant or as a parameter. Now the sixth step is to integrate the ordinary differential equation. In the sixth step you will integrate this problem. After integrating, you will get a solution which most probably depends on xi and eta. So in the step 7 you have to substitute the zeta, the eta and xi by x and y by the inverse transformation relations. So let's demonstrate this with the procedure with an example. We have ux minus uy is equal to u. So we are trying to calculate the general solution of this problem. So we will first construct the Lagrange subsidiary equations. So the Lagrange subsidiary equations are dx divided by p, which is 1, dy divided by q, which is -1, here the coefficient of uy is -1. Similarly, the du divided by u. We will ignore this quantity and we will use these two quantities. So uh, comparing the first two ratios, we see that dx by 1 is equal to dy by -1. This is really a simple case, and a simple integration will give us the solution to this problem. If you integrate this thing, this is basically integral of 1 dx is equal to integral of -1 dy. So doing the integration, you can see that the solution of this equation is x is equal to -y plus c1. This is constant of integration which is generated from these two integrals. This equation clearly tells us that x plus y is equal to c1. So this is our first characteristic curve. So we will choose xi is equal to x plus y. Now we will select the value of eta in such a manner that the Jacobian of xi and eta is not equal to 0. So the first choice is you can select eta is equal to y. This is up to you. If you select eta is equal to y, or if you select eta is equal to x, or if you select eta is equal to x minus y, it is okay. But the condition is that their Jacobian must be not equivalent to 0. So if we simply check eta is equal to y and check the Jacobian of xi and eta, we see that Jacobian of xy is equal to zeta x, xi x, xi y into eta x, eta y, and the determinant of this matrix. So the derivative of xi with respect to x is basically 1. The derivative of xi with respect to y is also 1. Similarly, the derivative of uh, eta with respect to x is 0, and the derivative of eta with respect to y is 1. In this way, if we check this Jacobian, we will calculate this determinant, and we see that this determinant is equivalent to 1, which is not equal to 0. So it means that the choices of xi and eta is correct. Now the next task is to convert the independent variable x and y into xi and eta. So u is a function of zeta, xi and eta, and we have calculated the derivative of u with respect to x as u xi into xi x plus u eta into eta x. So calculating the value of xi x and eta x, we see that xi x is equivalent to 1 and eta x is equivalent to 0. So we get ux is equal to u zeta. When we substitute this thing is equal to 1 and this thing is equal to 0, we will get ux is equal to u zeta. Now we will see that what is the value of the partial derivative of u with respect to y. So in our previous steps we have calculated uy as u xi into xi y plus u eta into eta y. So calculating using these values, the derivative of xi with respect to y is 1, and the derivative of eta with respect to y is again 1. So basically the derivative of u with respect to y becomes u zeta plus u xi plus u eta. Now substitute these two quantities into the partial differential equation, this one. We get u eta is equivalent to minus u. You substitute this thing here and minus of this thing here, so you will get u xi minus u xi and minus u eta is equal to u. So simply u xi and minus u xi will cancel each other, and you will have a function of the form u at eta is equal to minus u. This is called the canonical form of this partial differential equation. The canonical form of this partial differential equation is given by this one. Okay, if you are asked that uh, convert the following problem to the canonical form, so you will finish up here. And if you are asked that convert solve the problem by converting to canonical form, so you will do the step 6 and step 7 to construct the solution. So let's go to the step 6. Look at here, this is the first order ordinary differential equation. It can be written in the derivative form as partial u or partial eta is equal to minus u. After some mathematical manipulation, we can see that this equation is equivalent to 1 over y partial u is equal to minus partial eta. You can simply integrate, and you get the integral of this side is equivalent to natural log of u. The integral of this side is equivalent to minus eta and plus natural log of f of zeta. So why is this term here? Look at here. Here the quantity u depends on eta and xi. We are doing integration with respect to xi. So what are we getting to, what are we expecting as a constant? We are expecting the constant c must depend on the other parameter xi. So here I have written natural log of f of zeta. You can also write f of zeta only, but because this term is natural log of u, so if I write here is natural log of f of zeta, then it will be something easier to simplify and to calculate the main solution. You can also use f of zeta, f of xi only. Now let's do a little modification to this term also. We get natural log of u is equal to natural log of e power minus eta plus natural log of f of zeta. Okay, so using the property of natural logs, we can write natural log of u is equal to natural log of e power minus eta into f of xi. Now as the natural log is one-to-one bijective function, so from that property we can see that the images are only same if the pre-images are same. So from this equality we can write u is equal to e power minus eta into f of zeta. So we have obtained a solution which depends on two quantity eta and xi. Now the last step, step number 7, we will do the big substitution. We know we have calculated the expression xi is equal to x plus y and eta is equal to y. So if you use the value of eta is y and the value of xi is x plus y, and this problem, you will get the general solution of the first order ordinary differential equation. So let's revise the basic steps of this procedure. The first step is you have to make the Lagrange subsidiary equations. Simply you have to write dx divided by this term, dy divided by this term, and du divided by this term. The first two equations are important. You will ignore the third one. Comparing the first two ratios, dx divided by p, dy divided by q, it is possible that you can get a solution xi of xy is equal to c1. Now the third step is you have to select a function eta such that the Jacobian of xi and eta is not equal to 0. So the basic choice is you have to set eta is equal to x or eta is equal to y. Then it is most probably that the Jacobian is not equal to 0. Now as our main partial differential equation depends on x and y, so we have to change x and y into xi and eta. In our previous problem u depends on x and y, and we have changed u to be dependent on xi and eta. So we using this estimate we will construct the value of ux, and you will construct the value of uy. When you substitute these two values in the partial differential equation, this one, you will get an ordinary differential equation whose general shape is this thing. This is first order differential equation, and you can simply use any integration method. You can use any method to solve this problem. When you integrate and you construct the solution of the ODE, you will use the characteristic curves to do back substitution and get the solution of the problem. So I think this is enough for today, and inshallah in the next class we will study the conversion of hyperbolic, parabolic, and elliptical partial differential equations into its canonical forms. We will discuss the second order PDEs and its conversion to the canonical form. So take care. Allah Hafiz.